The chain rule. Let's take a look at the chain rule. If f and g are differentiable, then the composite function, f composed with g of x, which equals f of g of x, is differentiable, and the derivative with respect to x of f of g of x is equal to f prime of g of x times g prime of x. So in other words, the chain rule says to take the derivative of the outside function while leaving the inside function the same, then multiply by the derivative of the inside. So here is another way to think about it. If we want outside of inside prime, that equals outside prime of inside times inside prime. Let's go ahead and make sure we understand what we mean by the outside and inside function. Let's identify the outside and inside functions for a few different compositions. Here we have the quantity 2x plus 3 raised to the 7th power. So the inside function here is going to be what's inside the parentheses, 2x plus 3. So the inside is 2x plus 3, and it's inside of the function x to the 7th. So essentially what we're doing is replacing an x where the inside was. So our outside function is x to the 7th power. Let's try the next one. Here we have sine squared of x. We want to remember that we can think about this as sine x as a quantity squared. Now it's a bit more clear what the inside function is. The inside function is sine x. So sine x is placed inside of x squared. Is placed inside of x squared. And now finally we have e to the x squared minus 1. Now here the inside function is the part in the exponent of my exponential. So my inside is x squared minus 1, and it's inside of the function e raised to the power of x. So e raised to the power of x. So if we take our inside functions and put them into the x of our outside functions, we would obtain the composition. Let's take a look at a few examples. Here's the formula for the chain rule in general, and we're going to find each of the following derivatives using the chain rule. So here we have the derivative with respect to x of the quantity 2x plus 3 to the 7th power. Since I have a composition here, I want to identify what's the inside and the outside function. So the inside function is 2x plus 3, and the outside function is x to the 7th. Now, the chain rule says take the derivative of the outside function while leaving the inside function the same. So the derivative of the outside function, the derivative of x to the 7th, is 7x to the 6th. So I'm going to go ahead and start by saying that this equals 7, but instead of x to the 6th, I'm going to leave a big set of parentheses here. Because instead of putting x, we put the whole inside function exactly as it is. So I'm going to replace this with 2x plus 3. The rest of the chain rule says now I have to multiply by the derivative of the inside. That's g prime of x. So the derivative of the inside, the derivative of 2x plus 3 is just 2. So here we're going to go ahead and write times 2. This is the derivative applying the chain rule. Now all that's left is some simplification. So we can multiply the 2 times the 7 to arrive at our final answer of 14 times 2x plus 3 to the 6th power. Let's take a look at another example. In this example, I want the derivative with respect to x of the square root of 4x cubed minus x. I again have a composition. Before I start to apply the chain rule, I'm going to rewrite this as the inside quantity 4x cubed minus x all raised to the power of 1/2. So now, although we could follow the same process of writing out what's the inside and what's the outside, what I want to do is start to shorten this process. As we said, the outside function is going to be x to the 1/2, similar to how over here we had x to the 7th. Now notice what happened in this first example. Ultimately, we brought the 7 to the front, we left the inside the same, and we reduced the power by 1. That was the derivative of the outside while leaving the inside the same. So we're going to apply that process here to begin the first part of the chain rule. The derivative of the outside would be 1/2. We'll leave the inside the same as 4x cubed minus x. And we have to reduce the power by 1 in the exponent because we are applying the power rule. So we have negative 1/2. So here we've done the derivative of the outside, f prime, of g of x. Now what's left is to multiply by the derivative of the inside. So we're going to have times g prime of x is, by the power rule, 12x squared minus 1. So we're taking the derivative of 4x cubed and minus x here to get 12x squared minus 1. So now here we have our derivative, but it's not quite simplified yet. So let's go ahead and simplify this. The 12x squared minus 1 stays in the numerator, but the 4x cubed minus x to the negative 1/2 will move to the denominator. Notice that I rewrote the exponent of 1/2 after it moved to the denominator back into its square root form, and I kept the 2 in the denominator as well. Here are a few more examples. We're going to find the derivative with respect to t of 2 divided by the quantity t squared minus 1 to the 5th. We don't want to apply the quotient rule because the numerator isn't a function of t. What we can do instead is rewrite this as the derivative with respect to t of 2 times the quantity t squared minus 1 all to the power of negative 5. Now I can see that I have this inside function, t squared minus 1, and the outside function is 2t to the negative 5. So we can start the chain rule by taking the derivative of the outside. We will bring the negative 5 to the front and multiply to the 2, so we have negative 10. We'll leave the inside the same, t squared minus 1, but we reduce the power by 1, so we end up with negative 6. We've done the derivative of the outside, leaving the inside the same, and then times the derivative of the inside. So we're going to have times the derivative of the inside on this example is simply 2t. Since this isn't a binomial, it's just one term, I don't need parentheses. So I can leave it as just times 2t without parentheses. The last step is to simplify. So here I can multiply the negative 10 times the 2t. All of that will stay in the numerator. So negative 20t all over the quantity t squared minus 1 to the positive 6th power. We will bring just the binomial that's raised to the negative exponent to the denominator, and we'll multiply the negative 10 and the 2t and keep it in the numerator as our final answer. In this next example, we're taking the derivative with respect to theta of secant of 2 theta squared. Now here, when it comes to trigonometric functions, sometimes students make the mistake of thinking that this is the product rule, when in fact it is the chain rule that needs to be applied. This is secant of 2 theta squared, not secant times 2 theta squared. So we really have to be careful about our understanding of compositions versus products. So here, the outermost function is going to be the secant function. The inside function is 2 theta squared. So the derivative of secant is secant tangent. Now, instead of secant theta, I'm going to leave a blank space. So I'm going to put secant, and I'm going to leave a blank space, tangent, and I'm going to leave a blank space. Because what goes in there is the inside function. So we have secant of 2 theta squared, tangent of 2 theta squared. This is the derivative of the outside, leaving the inside the same. The derivative of secant was secant tangent, but we have to leave the inside the same. And then we have times the derivative of the inside. So the derivative of the inside is going to be, by the power rule, just 4 theta. And now, the only simplifying that I can really do is to take the 4 theta and put it in the front of the function. I cannot ever take anything on the outside of a trigonometric function and multiply it to the inside of the trigonometric function, nor can I ever take anything inside a trigonometric function and pull it out. So we're left with an answer of 4 theta secant of 2 theta squared tangent of 2 theta squared as my final answer. Here's a few more examples. So we're going to find the derivative with respect to x of sine squared x plus e to the power of x squared minus 1. Since each of these is added together, I can take the derivative of each part separately. Each part is going to require a chain rule. Here, I'm going to begin by rewriting this as the derivative with respect to x of the quantity sine x squared, and then plus e to the x squared minus 1. Anytime I have a trigonometric function raised to a power like this, it would help to think about it as sine x raised to the power on the outside, because that is in fact the outside function. So we're going to do each one here, one at a time. So here, the inside function is sine x, the outside function is x squared. So the derivative of x squared is 2x. So just bring the 2 to the front. So we're going to have this equals 2. We're going to leave the inside the same, which is sine x. And we're going to reduce the power by 1. So that makes this just sine x to the first. And now we have to multiply by the derivative of the inside. So sine x was my inside. Now I have to multiply by cosine x, the derivative of sine x. So I have now applied my chain rule to the derivative of sine squared x. So my biggest warning here is that the answer is not cosine squared x. That's a very common mistake from students early on, to think the derivative of sine squared x is cosine squared x. It is not. I have to think about it as sine x, quantity squared, and then the chain rule says take the derivative of the outside, bring the 2 to the front, leave the inside the same, and reduce the power by 1, then times the derivative of the inside. So times the derivative of cosine x. Now we'll go ahead and take a look at the second part, which also requires a chain rule because the inside function is x squared minus 1. Now the outside function here is e to the x. So the derivative of e to the x is just e to the x. But instead of putting x, we leave the inside function. So we're going to leave it as e to the x squared minus 1. So notice, it looks exactly the same, e to the x squared minus 1. The only difference is that we have to multiply by the derivative of the inside being what's up in the exponent of the exponential. The derivative is 2x. So here I have the derivative of each part, each one requiring a chain rule. All that's left is to simplify. So I have 2 sine x cosine x plus, I'm going to put the 2x in the front to have 2x times e to the x squared minus 1. Now what I want you to start to recognize, if possible early on, is are trigonometric identities. So 2 sine x cosine x can actually be simplified further. It can be simplified using the double angle identity for sine. This is the same as sine 2x. And then plus 2x e to the x squared minus 1. So this would be my fully simplified answer. In the second example, I have the derivative with respect to x of f of sine of x plus sine of f of x. This is a slightly different example because we have, in each case, one generic function. So here, f isn't a specific function, it's just some function f, and inside of it is sine x. On the other side here, I have sine, that's a specific function, of some generic function f of x. So here we can and still will apply the chain rule because I have two different compositions. Since they're separated by addition or subtraction, I can do each one separately. So here I'm going to go ahead and start out by saying, well, here I have f of sine x. The inside function is sine x. The outside function is f of x. Now, the derivative of f is simply f prime. So here I'm going to write f prime of, and I'm going to keep the inside the same, sine of x. So we have f prime of sine of x times the derivative of the inside, the derivative of sine, as we said earlier, was cosine x. So here I have f prime of sine of x times cosine x as the derivative of the outside, leave the inside the same, times the derivative of the inside. We now go ahead and take the derivative of the second part using the chain rule. So we'll have plus, on this example, f of x is actually the inside function. So the inside function is f of x, the outside function is sine x. The derivative of sine is cosine, but instead of putting cosine x, we have to put cosine of the inside function, cosine of f of x. And we can finish off by multiplying by the derivative of the inside, but this was a generic function. The derivative of f is simply f prime of x. So now we have the derivative, and there isn't anything we can do to simplify it. This is as simplified as it can get. So we just have f prime of sine x times cosine x plus cosine of f of x times f prime of x. And that's it. There's no simplifying that I can do on either of these. So sometimes people see, like, I have an f prime here and an f prime here, but they're not the same. This is f prime of sine of x. This is f prime of x. Here I have cosine x. Here I have cosine of f of x. So we really need to remember that our trig functions, we can't think of the cos part as its own separate thing. It doesn't make sense without an input. So cosine x is stuck together there, so I couldn't possibly pull out a cosine of f of x because these are two completely different quantities. In this example, I have the derivative with respect to x of tangent cubed of x squared minus x. Before we get started, anytime I have a trig function raised to a power, I want to remember that it's the entire trig function, so tangent of x squared minus x, all raised to that power of 3. So now here I have x squared minus x as inside of tangent x, but I also have tangent of x squared minus x all inside of x cubed. So I'm going to have to perform a chain rule within a chain rule. I always want to think about this as peeling off the layers. So the outermost function here is going to be x cubed, and then inside of that is that tangent function, and the final inside is x squared minus x. And I want to work from the outside in. So I want to start by taking the derivative of x cubed, which is 3x squared. So we're going to go ahead and have 3, but instead of x squared, I'm going to leave the entire inside function. So tangent of x squared minus x. So back to the original, what I've taken care of is the derivative of the outermost function. So that part is gone. So I'm going to put like check. I've taken care of that. Now we want to multiply by the derivative of the inside. Well, this inside here is its own composition. So the outside function here inside the parentheses is tangent, and the derivative of tangent is secant squared. So we're going to have times secant squared, but instead of x, we're going to have of x squared minus x, the inside here. So now we've taken care of the derivative of tangent. So that part's done. We left the inside the same. So the final thing is to take the derivative of x squared minus x and multiply by it. So we have the derivative being 2x minus 1. Since that's a binomial, two terms, I have to keep it inside of parentheses. So now this is my final answer. And there's really not much I can do to simplify. All I'm going to do is I'm going to keep the 3 in the front. I'm going to move the 2x minus 1 to the front. And now here, I'm done applying the chain rule, so I can take it back to tangent squared of x squared minus x. So keeping the exponent here. And then times secant squared of x squared minus x. And this is my final answer. In this example, I want to find y prime and y double prime given y equals the quantity x cubed minus 4 all raised to the 5th power. We'll start with the first derivative, y prime. That's going to require a very straightforward chain rule. So the derivative of the outside function here is going to be the power rule. We're going to bring the 5 to the front, leave the inside the same, x cubed minus 4, and reduce that exponent by 1. So that's that power rule. So 5, the inside to the 4th. And then the rest of the chain rule says multiply by the derivative of the inside. So the inside of the original function, x cubed minus 4, has a derivative of 3x squared. So times 3x squared. And we will simplify this by multiplying 5 times 3x squared to get 15x squared times the quantity x cubed minus 4 all to the 4th power. So this is y prime. Now we need to find the second derivative, y double prime. Looking at this first derivative, we actually now have a product of two functions of x, 15x squared times the quantity x cubed minus 4 to the 4th. We will need to apply the product rule, and within that process, do another chain rule. So we're going to have y double prime is equal to, we'll leave one function alone, so 15x squared times the derivative of the second function. Well, that's another chain rule similar to the first one we did. So we're going to bring that 4 to the front, derivative of the outside, so 4, leave the inside the same, x cubed minus 4 to the 3rd power. We don't want to forget that exponent, so we brought the 4 to the front, left the inside the same, reduced the power by 1. That's the derivative of the outside times the derivative of the inside to finish out that chain rule. So times that 3x squared. We're halfway done with the product rule, so now we have to do plus, and then we'll leave that second function alone this time, x cubed minus 4 to the 4th, and then times the derivative of that first function now. So the derivative of 15x squared is just a power rule, so we'll have 30x. From here, we want to simplify. Let's remember that this is two terms. Terms are separated by addition or subtraction. And what we can do on this one is we can simplify each term first to sort of help us out. So let's multiply all of the numbers involved in this first term. So 15 times 4 is 60. 60 times 3 is 180. So I have 180. Then I have x to the 4th power, x squared times x squared. And then I have that quantity x cubed minus 4 to the 3rd. And then plus over here on the right-hand side, that term, I'm going to put 30x quantity x cubed minus 4 to the 4th. So we did a little simplifying to each term first, and now I want to factor out what's in common with each term. So between 180 and 30, I can factor out a 30. Between x to the 4th and x, I can take out one copy of x, so x to the smaller exponent. And between x cubed minus 4 to the 3rd and to the 4th, I can pull out the smaller of the two. So for that binomial, I'll pull out x cubed minus 4 to the 3rd, the smaller exponent. And then let's figure out what we're left with. I'm going to use brackets. And I'm going to say, well, from the first term, if I factor out 30, that's dividing it out, I'm going to have 6 left over. So I'm going to have 6 x cubed. So if I take out one copy of x from the 4 that were there, I have x cubed left. I took out the whole binomial here to the 3rd power. So that's it for the first term. And now plus the second term, I took out 30x, but only 3 copies of x cubed minus 4. So I'll have one copy left, x cubed minus 4, to the 1st power. So there's no need to put parentheses around it if it's just to the 1st power. So that's all I have left, and inside those brackets I have some like terms, so I'm going to write my answer as 30x times the quantity x cubed minus 4 to the 3rd times 7x cubed minus 4. And there's no other factoring I can do, so I am done. In this example, I want to take the derivative with respect to x of 2x all over the cube root of the quantity x squared minus 1. So here, the way that it's currently set up, I would need to apply the quotient rule. And within the quotient rule, I'm going to be doing a chain rule because of the quantity in the denominator. I'm going to start by rewriting this as the derivative with respect to x of 2x all over the quantity x squared minus 1 to the 1/3. And I do have an option of bringing this quantity to the numerator and making this a negative exponent and then applying the product rule. That is a choice, but because we just applied the product rule, let's practice the quotient rule. So I'm going to go ahead and start by applying the quotient rule, which says we're going to start with the bottom function, low d high. So low, we're going to leave x squared minus 1 to the 1/3 alone, times the derivative of the numerator. Derivative of 2x is 2. So we have low d high minus high, the top function 2x, d low. The derivative of the bottom function will require a chain rule. So we're going to take the derivative of that outside function, which is a power rule. So I'm going to bring that 1/3 to the front. 1/3, leave the inside the same, x squared minus 1. And then I have to finish out the power rule, which means subtracting 1 from 1/3. And that's going to give me a negative 2/3. So we did the derivative of the outside while leaving the inside alone, then times the derivative of the inside. The derivative of x squared minus 1 is just 2x. So we did low d high minus high d low, derivative of the bottom, and we have all of that all over the bottom squared. So I have x squared minus 1 to the 1/3 squared. And from here, this is the derivative, but we want to go ahead and simplify it. And we want to simplify the numerator, recognizing that it is 2 terms. Terms are separated by addition or subtraction, so I have these 2 terms separated by subtraction. And to simplify here, I want to factor out what's in common in both terms. So we'll start with the numerical values. So that's in the first term I have a 2. In the second term I have a 2, a 1/3, and a 2. So I can factor out a 2, and the second term has an x squared, an x and an x, but the first term doesn't have any x's that are part of this, so I can't do anything with that. And they both have this binomial, x squared minus 1. One is to the 1/3, and the other is to the negative 2/3. So I'm going to factor out x squared minus 1 to the negative 2/3. Remember, we always want to take out the smaller of the two exponents. So a negative number is smaller than a positive number. And then we will see what's left over. So when we see what's left over, I use brackets, although parentheses are fine. So from the first term, I took out the 2, and I took out x squared minus 1 to the negative 2/3. So I'm going to have x squared minus 1. It was to the 1/3, but we're taking out, which means subtracting, so minus negative 2/3. So I have x squared minus 1, and it had a 1/3, but when we factor out negative 2/3, we're really subtracting that. So 1/3 minus negative 2/3, well, 1/3 minus minus becomes plus 2/3, and 1/3 plus 2/3, well, that's just a 1. So all of this just simplifies to a 1 right there. All right, so let's move on. What's left over from the second term? Well, we took out a 2 and x squared minus 1 to the negative 2/3. So what do we have left? We're going to have a 2/3 left, an x squared left, and that's it, right? Because we took out one of the 2's and then the entire binomial to the negative 2/3. So that's all that's left there. And now in the denominator, I have the quantity x squared minus 1 to the 2/3. So these exponents would multiply. All right, let's do two things at once here. So I have x squared minus 1 to the negative 2/3. Well, a negative exponent attached to this binomial will drop the binomial down to the denominator and make this a positive exponent. So what do we have here? I'm going to leave the 2 on the top. On the bottom, I'm going to have x squared minus 1 to the 2/3, and then another x squared minus 1 to the 2/3 from this one being dropped to the bottom. And then what's happening inside here? Well, like I said, this was just x squared minus 1 to the first power. So this part right here, maybe let me pull it to the side. Inside these brackets, this is really just x squared minus 1 minus 2/3 x squared. So there was no need for parentheses because it was really just to the first power. And so there's like terms that are going on here, right? 1x squared and minus 2/3 x squared, that's 1/3 x squared. So I have 1/3 x squared minus 1. Let's move this over a little bit. All right, so what we could do from here, on the bottom, I can, since these have the same base, I can add these exponents together. I also could have just done that right away if I wanted, made this x squared minus 1 to the 4/3. And then up here, I have this 2 times 1/3 x squared minus 1. Now to be fully simplified, we really don't want a 1/3 in a numerator or denominator. We don't want a fraction within a fraction. So what we can do is clear those fractions by multiplying the top and bottom by 3. So we're going to distribute this 3 in to this binomial here, and that's going to give us, well, that 2 is going to stay in the front, and that's going to give us an x squared minus 3 all over 3 times x squared minus 1 all raised to the 4/3. In this example, I have the derivative with respect to x of 3x over sine cubed x. The way that it's set up, we could jump straight into a quotient rule because I have a function of x over a function of x. But instead, on this problem, I'm going to think about it as the derivative with respect to x of 3x times cosecant cubed x. I didn't take a derivative there. I applied a trig identity. 1 over sine x is cosecant x. So 1 over sine cubed x can be rewritten as cosecant cubed x. So this is now a product rule situation, and within that product rule there will be a chain rule because this is cosecant x all cubed. All right, so let's get to it. Let's apply the product rule. We have the first function, 3x, times the derivative of this cosecant x all cubed. So we have to do the derivative of the outside. We'll bring that 3 to the front. We'll leave cosecant x alone and subtract 1 from the exponent. So I did the derivative of the outside, that was a power rule, while leaving the inside the same, times the derivative of the inside function. The derivative of cosecant is negative cosecant x cotangent x. We don't want to forget the x right here. Cosecant x cotangent x. All right, so where are we at in this process? We left the first function alone. We took the derivative of the second function, which required a chain rule. Now plus the second function, which is that cosecant cubed x, times the derivative of the first function. And the derivative of 3x is just 3. All right, so the simplifying here, let's simplify each term here first, just to kind of see what's going on. I do have a negative 9x, so I have this 3 times 3, I have this x that's here. Total cosecants, I have cosecant cubed, because I have cosecant x all squared, so that's 2 copies and a third copy here. So I have cosecant cubed x, and then 1 copy of cotangent x, and then plus 3 cosecant cubed x. So now what's in common in both here is I can factor out a negative. So usually when the first term is negative, we factor out a negative. So I can factor out a negative. I can take out a 3, that's in common in 3 and 9, and I can take out a cosecant cubed x. And what would be left here is 3x cotangent x. So I took out a negative 3, I divided that out. I would have a positive 3 left over. I would have this x left over and this cotangent x. And then over here, since I divided out a negative 3, I would have a negative 1 left. So this is my simplified answer, as we can get. Now we want to find the derivative with respect to x of cotangent of the quantity 2x cubed over 4 to the x. So here we have to start with the chain rule, and within the chain rule we're going to apply a quotient rule. So we have to do the derivative of cotangent first, that's the outer function. So the derivative of cotangent is negative cosecant squared, and then we leave the inside the same. So that's 2x cubed over 4 to the x. So we've done the derivative of the outside, leave the inside the same. Now times the derivative of the inside, but the inside is a quotient. And we could rewrite it so that it's a product, but let's practice the quotient rule again. So the derivative of this inside here by the quotient rule is going to be low d high. So low is 4 to the x. D high, the derivative of 2x cubed, is 6x squared. And then minus high, which is 2x cubed, times d low, the derivative of 4 to the x, is 4 to the x times natural log of 4. And so we're done with low d high minus high d low all over low squared. So that's 4 to the x all squared. And from here we can do a little bit of simplifying. We'll say negative cosecant squared 2x cubed over 4 to the x. And now in the numerator here, right, we want to recognize that that's 2 terms, and we want to factor out what's in common. We can take out a 2, an x squared, and a 4 to the x. And then we would be left with, from this first term, just a 3. If we divide the 2 out of there, we have just a 3 left. And then minus, let's see, on this right-hand side, we would have the 2 gone. X squared was taken out, so 1 copy of x is left. The 4 to the x was taken out, so we have the natural log of 4 left. And then all over 4 to the x squared. Now, because 4 to the x is a factor in the numerator, I can cancel it. So 4 to the x with one of these 4 to the x's on the bottom, making that just an exponent of 1 on the bottom. So I couldn't do that sooner. One of the common mistakes, right, is people want to cancel like this 4 to the x here automatically with this one. I cannot do that because I have 2 terms, right? I can only do it here. Notice that this is a factor, right? This is multiplication. Right here, the subtraction is what blocks me from canceling any earlier. And so I'm going to write negative cosecant squared 2x cubed over 4 to the x, and then times 2x squared times 3 minus x natural log of 4 all over 4 to the x. And that's really the best I can do there. And here I have the derivative with respect to y of e to the 3y all over the quantity 1 minus y over 2 all to the 4th power. So this has 2 chain rules involved. The numerator is a chain rule and the denominator is a chain rule. But we actually have to start by applying the quotient rule. So this is a quotient of 2 functions of y. So I do have to apply the quotient rule, and when I get to the derivative of the numerator and the denominator, those will each require a chain rule. Now we could go straight to the quotient rule, or we can rewrite this so that we have the derivative with respect to y of e to the 3y times 1 minus y over 2 to the negative 4th. Well, actually, I'm going to write this as 1/2 y to the negative 4th. I'm going to rewrite y over 2 as 1/2 times y. So I can think about this as a product rule. So let's do that. Let's go ahead and leave the first function alone, e to the 3y, times the derivative of the second. Now this is a power rule. We'll bring that negative 4 to the front. We'll leave the inside the same, 1 minus 1/2 y, to the negative 5th, so we're going to subtract 1 from the exponent, times the derivative of the inside. So the derivative of 1 minus 1/2 y, that's just negative 1/2. And so then I'll have plus the second function, 1 minus 1/2 y to the negative 4. And then I have to take the derivative of e to the 3y, and that is a chain rule. So we have e to the 3y times 3. So the derivative of this exponential is just the exponential, and we leave the inside the same, but then the derivative of the inside, 3y, is just 3. So we had 2 chain rules, but that was within this product rule. And then we simplify. So we want to see these 2 terms here. Let's simplify each term first. Let's see, this negative 4 and negative 1/2, that's 2. 2e to the 3y times the quantity 1 minus, take it back to y over 2, to the negative 5th, and then plus 3e to the 3y times the quantity 1 minus y over 2 to the negative 4. And let's see, what's in common in both? They have an e to the 3y, and I'm going to take out a 1 minus y over 2 to the negative 5th. Remember, the smaller of the 2 exponents. And then what's left over? Well, a 2 is left over from the first term, and that's it. We took everything else out. From the second term, I'm going to have a 3 left over. I took out e to the 3y, and from 1 minus y over 2 to the negative 4th, I'm taking out, right, it's minus negative 5. When we take it out, we're subtracting that exponent. So minus minus, that becomes a plus. So what's going to happen here is I'm just going to have 1 minus y over 2. I'm going to erase that and leave it as just a 4 up there. Negative 4. So this is just to the first power because it was negative 4 minus negative 5. Negative 4 plus 5 is 1. And from here, let's see, I would have e to the 3y is going to stay in the numerator. I'm actually going to work to the right here. So I'm going to have e to the 3y in the numerator. What'll drop down to the denominator is that 1 minus y over 2 to the 5th. And also in the numerator, let's see, this 3 would distribute. So that's 3 minus 3 halves y. And 3 and 2 are like terms, so we're going to have 5 minus 3 halves y. Now, is this fully simplified? No. Whoops, we do have like a little bit of an issue because of some of those fractions, but there's really no fixing this y over 2 that's in here. I could clear the 3 halves by multiplying the top and bottom by 2, but we'll just go ahead and leave our answer like this. This would be good enough to solve if we were trying to solve this equation. We're not, we're just simplifying, but we'll just go ahead and leave our answer like this.